Good evening, everyone. This little video of Mr. Dwight Doodles is probably the most challenging of the required practicals, and it is this one here. That's enzymes required practical. So let's begin this story. In this experiment, we have a molecule called starch. Now, it's a polymer, which means it's made of lots of individual units, and these individual units are called glucose, aka a simple sugar. So if we look straight away at what is starch made of, we can see starch is made of glucose. What's the difference between glucose and starch? Well, starch is bonded together to make a large insoluble molecule, where sugar is soluble, dissolves in the blood, and that is what we need within our bodies. So let me introduce you to a little friend of ours. Now, obviously, enzymes do not look like this. They do not look like Pac-Men and women. But for the purpose of this story, that's our little Pac-Man. And what the Pac-Man does, our enzyme, and this has a name. This is called amylase or amylase. And what it does is it breaks down the bonds of the starch molecule to produce glucose. So starch to glucose. That's the first part of the knowledge that we need to be successful within this required practical. There's so much going on. This here, we've all seen these in the science lab, is what we call a white tile. It's got wells to hold solutions or liquids that we can put things in. So in this investigation, it's all based on this. How fast does this break down this into this? And there are two things the investigation can look at. Generally, that's pH, which we'll talk about, and temperature. But how does the investigation work? We're going to change something, we're going to measure something. So then what we're going to actually measure is time. How quickly does this, the enzyme amylase, break down starch into this? And we use something called a reagent. This is a chemical that we've all used, and it's called iodine. Iodine tests for the carbohydrate starch. Iodine is orange. I don't have orange in my pen selection, so I'm going to put a drop of orange iodine into the well. If I now place my starch into the iodine, it will turn blue black. Don't know why they put the blue, because it is definitely black, but it goes blue black, and that tells you starch is present. If I was to then put a drop of iodine into this well, and I add glucose into the well, nothing happens. Nothing happens because iodine tests for starch, it doesn't test for glucose. So the iodine, which is orange, remains orange in the presence of sugar. So let's have a look now as to what we actually do within this experiment. Let's bring it back to our white tile, or with the wells in. I'm just going to do 6. Right. What we're going to do is we're going to add our iodine into the wells, just a drop of that. And obviously, why do we do practical science? Where it's to look for a relationship. The relationship is what we change and what we measure. So in this investigation, we're going to change the pH. That's the presence of hydrogen ions within the solution. How does pH affect the speed or the rate by which amylase breaks down starch into glucose? What we're looking for is it to start black, and the quickest rate is going to be the one that starts black in the well and then turns orange really quick. It's turning orange really quick because all the starch is gone. All that is left is the glucose, because the amylase has been proficient in breaking it down. What are we going to measure? We're going to measure the time for the starch, which will be black, to turn the black to turn orange. When it's turned orange, there's no starch present. So we'll do seconds for that. All right. So now what we get is our boiling tubes. I've done 4. In our boiling tubes, we're going to add our starch. We'll keep consistency. It all looks the same. There it is. Now this is a solution, so there's lots of them in there. Next up, we're going to add our solution of enzyme. There they are. Enzyme, enzyme, and enzyme. And what's going to happen is the enzyme is going to break down the starch. But they're all saying we haven't changed anything in this one. So now what we do is we're going to introduce our pH. It's got a funky name called buffer, which is just another way of saying a solution. And so because we need to have our control variables, in this our control variables will be our volume of starch, our volume of enzyme, amylase, and our volume of acid, alkali. Okay, right, and then what we do is as follows. Let's say this is pH 5, 6, 7, and 8. These are our pHs. We add it all together, you can stir it, and then what we do is someone is on a stop clock. There's our time, 0, 0. We start the clock. So the first thing we do is we take a pipette, we go into our solution, and we place a sample, let's say a meal sample of what's going on in there. Now, due to the pH, has the pH prevented the enzyme from breaking down the starch? Well, at 0 seconds, we would expect it to be black. Why is that? Because starch will be present. After 30 seconds, we go back in, we take out, so that's 0. This one's 30 seconds. We put our solution in there, and it's still black. Why is it black? Well, we're still here, it's still pH 5, because we've still got starch present. 1 minute, same again. We take out, we put it in there, it's still black. Then after a minute and a half, or 90 seconds, we drop it in, stays orange. It stays orange because all of the starch has been broken down by the enzyme, and therefore we stop the clock. And we would record 0, 30, 60, 90 seconds for pH 5. What we then do, empty the wells, put the iodine back in, and we start again with pH 6. Start the clock, 0. Take a pipette, 1 ml, in it goes, still black. Same again, 30 seconds, black. Why? Starch still present. In it goes, but in 60 seconds it stays orange. Why does it stay orange? It stays orange because the enzyme amylase has broken down the starch and all that's remaining is glucose. That is tricky because there's a lot going on. Obviously, we need to repeat it for each of the different pHs, calculate a mean, remove any anomalies. That's pH. It could throw in temperature, and obviously with temperature, you'd place these, you wouldn't change the pH buffer, so you'd remove that, take that away, or you'd use the same pH buffer of 7, and then you place them into a water bath, and then you'll change the temperature of the water in the water bath. Same principle, we take out and do. Now, a common question that you will see is, this is what was completed in the masterclass, but we've got a lot of doodlings on there from the masterclass earlier. So I'm going to just explain what the question says on the other side. Table below shows the results of the investigation. The investigation prior just shows you what I've gone through. This time they're changing temperature and they're measuring the time taken until the iodine solution stays yellow-brown. So that there is our first obstacle, yellow-brown, because we know iodine is orange, but it could be yellowish or it could be brownish. And obviously it's all subjective. So what we're doing is we're changing the temperature and then we are measuring the time it takes for the starch to be broken down, which is where it goes from black to orange, or here yellowish brown. Now, if we look, 5 degrees did not become yellow brown. That means there's no glucose present, which means that there is no breakdown of starch. It remained black. This question asks us to do this. It asks us to explain the result at 5 degrees and the result at 80 degrees. Because it is an explain question, we must state something and because. State, at 5 degrees, the solution did not become yellow-brown, it remained black. It's black because starch is still present. You could write it hasn't been broken down. Now this is where you have to explain why. Well, inevitably, the amylase enzyme has to meet the starch molecule. They have to meet. They're all floating around. They must collide. But it's at 5 degrees. Now 5 degrees gives you a huge hint that there's the enzyme, little smiley face. Remember, they don't have a little smiley face. There's the starch molecule. They have to collide, and they're moving around within that solution. But at 5 degrees, they lack enough kinetic energy to collide. And when they collide, a reaction will take place, but it hasn't because they don't have enough kinetic energy in order to collide to therefore break down the starch into glucose and go from black because that's what starch goes, because glucose. It then asks at 80. Well, at 80 degrees, this is where you have to talk about specificity in your terminology. There's our enzyme. Again, doesn't have a little smiley face like that. At 80 degrees, it has too much energy, and what happens is the 3D active site changes its shape. It is distorted. It is no more complementary. That's the key word here, complementary, because starch fits like a key in a lock into the active site. But because the heat has transformed the active site's three-dimensional shape, the substrate, which is starch, will not fit and therefore will not be broken down. And then the final key term here is, what is that called when the three-dimensional active site changes shape? That is called denatured. That is a classic question of explaining the results of the required practical on enzymes. I hope that helped. Till next time.